This is tutorial 8, question 7a. In this question, we are given a matrix A that is 3 by 3, and we are given its 3 eigenvalues. The eigenvalues are distinct, therefore the corresponding eigenvectors are distinct, as in independent, and therefore we have a complete set of bases. So remember our previous tutorial. A equals to P d P minus 1, where P is the columns of eigenvectors. So now I'll write for you. So this is V1 and the corresponding V2 and then V3, and then we have our D here. So we have 1 here for lambda 1, and we have lambda 2 and lambda 3. So we have 1 and 2 over 3 and 1/3 with 0 entries. Therefore, the last one is P minus 1. So we have P, D, and P minus 1. Alright, so what we are going to do now is that we are trying to do as before. What happens in AK? Why AK? Well, the equations that we are given is this. So let's start with x of 1 is equals to A times x of 0. X of 2 is equals to A times x of 1 is equals to A times x of 0 is equals to A square x of 0. And therefore now you see the pattern is equals to A cube x 0. Therefore we are interested in AK. So therefore x of k plus 1 is equals to AK x of 0. Okay, that's the pattern. Alright, I should xk plus 1 here. Alright, therefore, so we have therefore AK x0 equals to x of k. Right. So what about when we talk about the general solution? Well, and we're given x naught. So what do we do? Well, so we need to do this. So x naught is 1, 11, and minus 2 here. So what we need to do is that we have seen in the previous tutorial, it will be P dk P minus 1, the column vector x naught, to get xk. And now we can fill up the rest, and I guess that'll be good enough. So maybe we fill up the matrix. So I write down the whole matrix. So this matrix is P, this matrix is D, this is P minus 1, so you can see the minus 1 here, and this is x of 0. Now this is a very interesting operation, P minus 1 times x 0. Please refer to the change of basis in Lay's 5th edition, chapter 4.7, page 241 to 244. You can see the change of basis. The change of basis is this. The vector x in the standard basis related to the x in the particular basis is P, and this we write as x0 in the P basis. Okay, so therefore x0 in the P basis can be calculated as inverse of P times x0, and you see this here, this picture, this equation here. And in fact, you'll realize that what we just did was that we changed the x0 from the standard basis into the P basis, multiply by D, and then what about PD? Okay, what is PD? PD changes the information in the p basis back to the standard basis. Okay, so many things is happening here. You realize that when we did the problem in this way, we first, let me repeat, we first change the standard basis to the p basis. We perform the transformation using d in the p basis, and then finally we transform the answer back into the standard basis. So that's what's happening here. Okay, if you can follow this argument, then you understand the change of basis and it's used in the eigenvalue decomposition. Alright, let's compute this guy. What is x0 in the p basis is p minus 1 x of 0, and by brute force you can compute the answer, and the answer is, so I simply use MATLAB to enter p, and then I get p minus 1 times 111 minus 2, which is x0 here, and I get 213. Right, so I'll just write this down. Of course, you have to figure out how to do this by brute force, but so this is my answer for 213. So what do we do now? We want to do this, which is d times 213. Now what is d? D is a diagonal matrix, so that's relatively easy. What we'll get is that we'll get 2 times 1k, and 3 by 3, 3 by 1, we get 3 by 1. So the second one is 2/3 k by 1, and the last one is 1/3 k by minus 2. So this is what do you call that? This is d times p minus 1 times x0. Now we're almost there. You realize that as k tends to infinity, these values tends to 0. So it leaves us with this value here, 2 times 1k is infinity, so these are all 0, and therefore the final answer is x of k is equals to minus 2, 2, 1, which is simply the first column, the first eigenvector here, the first column multiply by 2, 1, k. Okay, and k doesn't matter as k tends to infinity because it's 1 to the power of infinity. Alright, I think that's the answer. Right, I realized I made a small mistake here. This should be 213, and 213 came from x0 in the p basis. Okay, so this is 213, but it doesn't matter because what happened is that as k goes to infinity, this becomes more significant, and this becomes 0, and 0 times whatever value. So that's why I couldn't see the mistake then. Right, so that's all we have here for this question. Thank you.